Hi everybody, welcome to another video in Statistics, Chapter 6, Discrete Probability Distribution. So we talk about discrete and continuous variable before in Chapter 1. Now more definition. A random variable is the numerical measure of the outcome from a probability experiment. So this value is determined by chance. So the random values will take the values and for each values there is associated probability to it. We see some example later. Random variables are denoted using the letter, capital letters such as X. A discrete random variable has either finite or countable. So when we talk about discrete, I have two possibilities, finite or countable. The values of discrete random variable can be plotted in the number line with space between them. Right. So discrete could be 1, 2, 3, 4, 5 counting number and could go indefinitely. Continuous has infinite many values. So we can say it doesn't have to be infinity. But for example, if we set the whole line from 0 to 1, if we talk about the whole line, it will be continuous. Discrete, the line will not complete. Will be space in between each point. So we might say, let's say 0 and 1, 0.5. If we talk about those 3 points, that will be discrete. If we talk about every point from 0 to 1, that could be continuous. I mean, it just could be 0 to 1, could be any range. Right, so discrete is finite and countable. Continuous is continuously has infinitely many values. Right, determine whether the following random variable is discrete or continuous. I state the possible values. So the number of light bulbs that burn out in a room of 10 light bulbs. So if we say the number of light bulbs be x, so that is the random variable. So x can take the values of it have 10 light bulbs. So the number of burnout could be anywhere from 0 to 10. So 0, 1, 2, all the way to 10. And this is discrete. The number of leaves of a random selected oak tree. Again, if we let the number of leaves as a variable x, and it could be no leaf 1, and the numbers here in that case might not go almost very high number, but still it's going to be discrete. And the length of cones to 911. Now this one, it could be it's not going to go indefinitely, but it could be any time. You can say like 2 minutes and 1 second, or 2 minutes and half of a second. So pretty much any value is possible in the. So if we let the length in time, let's say x, could be anywhere from 0 and could be 1.1 minute, or I mean pretty much any number. It does not go to infinity, however it can take any values, so it is continuous. So this chapter we focus on the discrete random variable. Right. Next we define the probability distribution. The probability distribution of a discrete random variable x provide the possible values of random variable and their corresponding probability. So they have the values of x, and each values of the random variable there will be a corresponding probability. Probability distribution can be in the form of the table, graph, or mathematical formula. So here, for example, that x represents the number obtained from rolling not so fair die. So rolling a die, we may have from 1 to 6, and each one have some different probability to it. So these are the values of the random variable with the corresponding probability. Next, rule for discrete probability distribution. So let P of x denote the probability that a random variable x equal to x, then the sum of all P of x is equal to 1, and the probability have to be between 0 and 1. Of course, we talked about this already. Probability of any event have to be between 0 and 1. 0 being impossible and 1 being certain. And each probability of each values have the sum of all of that have to be 1. So let's look at here's some example. So which one of this is a probability distribution? So can this be a probability distribution or not? So when we look at the first example here, all of this between 0 and 1, so that check. All we need to check is that all of them need to add up to 1. So we just add all of this up. 0.16, 0.18, 0.22, 0.1, 0.3, and 0.01. All right. As you see, the sum of all of this is only 97, so it's not 1. So because the sum is not 1, this is not a probability distribution. So this is not a probability distribution. Right. All of this between 0 and 1, so that is at least that one is good. So that box is checked, but the total is not 1, so it's not good. Next, when we look on of this values is less than 1. So it's a P of 5 less than 0, so it's not a probability distribution. Probability distribution has to be on the probability has to be between 0 and 1. So this is not a probability distribution. Next, all of this between 0 and 1, so that's one's good. And we just need to make sure that they add up to 1. So 0.16, 0.18, 0.22, 0.1, 0.3, 0.04 is equal to 1. So the sum of all the probability is equal to 1. So this one check. So we have both of them. So this is a probability distribution. Oh, so right, one more time. Between 0 and 1, and probability of each values have to add up to 1. Right. Now we have a probability distribution or distribution, so we can find some statistic of that. So the first one is the mean. The mean of the discrete random variable is given by the formula, the sum of all the x times p of x, where x is the variable of the random variable and p of x is the probability of observing x. So once again, we have the example of a die rolling either 1 to 6 with corresponding probability. Now compute the mean. So we have x, those are the values, and p of x are the probability, corresponding probability. So what we do is we multiply across and then add all of them up, pretty much. So we have the values times the probability. So this I just say the product. So 1 times 0.2 is 0.2. 2 times 0.15, 0.3. 3 times that, 0.45. 4 times that, 0.6. times 5, 0.75. And 6 times that, 1.2. Right. And we just add all of this up. So it's 3.5. So this is the mean of random variable x is 3.5. Right. Now if we use a calculator, there's a lot of way to do this. If we have stat, edit, hit enter, and we have the two lists. One list, and then the second list is for the probability. The first list is for the values, second list for the probability. Right, and then quick second mode. Now we will start calculate one variable statistic, list 1, and the frequency list is list 2, and then just calculate. Right, we have the mean of 3.5. right? Yeah, this is the mean. Of course, we can also use different way. Let's go back to the list. We have list 1, list 2, and then we can go to list 3. When list 3 is highlighted, we enter second 1 for L1 times second 2 for L2. So we multiply straight across. Now we just need to add all everything in list 3, right? So second mode. To add, we go to stat, calculate, second stat, go to math, option number 5. Once again, second stat, go to math, option number 5, and then we add everything in list 3. Of course, we have the same thing, right? So whether we use by hand calculator using one variable statistic, just go to StatCrunch for that as well. Just bear with me for can I type it? Yeah. And then we'll start summary stat. Calculate summary stat columns. We need two variables, and what do we need to calculate? The mean. So the mean is do this again. Start calculate summary stat group and bin data have to be that. First variable and the second variable will be counts rollout distribution, and we'll calculate the mean. Okay, so that doesn't work. Let's try again. have to pause the video because in the StatCrunch here doesn't have the direct calculation. All we have to do is just click on one of the cell and we go to data and we compute expression. So what we do is we're going to build expression. Just go to the sum, we then add sum, and then we say variable 1 and then times variable 2 and just that compute. Yeah, that is 3.5. So it's more like in Excel. Right, now back to the note. Now interpretation of the mean of discrete random variable. Suppose an experiment is repeated n independent times and the values of random variable x is recorded. As the number of repetition of the experiment increases, the mean values of n trial approaching to the mean of the random variable x. In other words, let x1 be the values of the random variable x. After the first experiment, x2 be the random values of x after the second experiment, and so on. So it's the mean and of the that values. So the mean after n trial will get close to the actual. Yeah, so the mean after n trial and the mean of the random variable will get close to each other. And the proper name for it we will define as what we call the expected values. So the mean of the random variable represent that could happen, expect to happen in the long run is called the expected values. So this is the mean of what about to happen in the long run. For example, if you expect, if we having a child, if a family has a child, for example, the chance for it to have a boy is 50% and the girl is about 50%, so about 50%, right? So in the long run, if we have if a family has 10 children, we expect to have 5 boys and 5 girls. Or if we have 9 children, then we expect to have 4.5 boys, and of course we not really have 4.5. We cannot have that. What we have to say is, in the long run, if that just keep repeating for a family that has 9 children, so the mean is about 4.5. It doesn't mean we can get exactly 4.5, but in the long run, it is about as close as possible to 4.5. So we have more example to that, and there will be a better example. But for now, the expected values is just the mean of the random variable. Right. Let's look at this example. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. This policy has premium that must be paid annually. Suppose a life insurance company sells $250,000 one-year term life to a 4-year-old female for $530, and the statistic says that the probability that person survive for the whole year is that much. Compute the expected values of this policy to the insurance company. So this is with respect to the company, right? Not with respect to the policy holder. This is with respect to the insurance company. Right, so there's only 2 outcomes here. Number 1 is the person die. If it's dead, what company will have to pay? Regardless, the company will get $530. That's a plus. The policyholder pay the insurance company, so this is a plus 530. But because the person dead, the company have to pay out $250,000. So plus that much and subtract that much. In the case of that, the probability is 0.999791. So if that person is dead, the chance for that person alive is the company will get 530 and does not need to pay out anything. And the chance for this to happen, remember, a person either dead or alive, so they are mutually exclusive. I should say they're complement to each other. So just set 1 minus 0.99791. And that gives us 0.00209. And now we multiply straight across and then add them. The expected values will be the sum of this column. Have expected values. Right, first I have negative 530. This is the negative sign, not that subtract. 530. I'm sorry, gaining $530 regardless, but have to pay out $250,000. Right, with that, multiply by 0. I got them backward, did I? Sorry. I put the probability backward. The percent of the person who dies 99.791. So I put them backward. Sorry. Yeah. So survive the year is that much. Right. One more time. So I have this number times 0.00209. So that's minus $521.39. And now, if the person alive, the company will get 530 and doesn't have to pay back anything. Now we add these two numbers. I have $7.5. So that means in the long run, the company expected to get $7.5 for each policy. But like I said, this is expected values. A lot of things could happen if there is a pandemic or something. A lot of people die. In that case, the company will lose a lot of money. But what they will do when they make a policy, they based on the statistic of that person, the chance for that person to live, or chance for that person to die, and they make the money, and so they choose something that they can make a profit out of this, and it does. In this case, the profit will be $7.5 for the type of the policy holder. Right, continue. Suppose you pay $1 to roll a fair die, with understanding that you will get back $3 rolling a 1, get back $2 for rolling a 2, and nothing otherwise. What is expected net winnings? So we'll make a table like what we did. The first one is the outcome. The second is the values. The next one is the probability. The next one is the product of the values times the probability. So we say values times probability. Right. Now, we pay $1 to play that game. So when we do this, we have to look at the perspective. Like the previous example, we talk about the expected values from the company perspective. This is what is your expected value. So this is from the player. So when they pay $1, so regardless, they pay $1 each. Now the outcome, if you get a 1, winning $3, and to get back $3. If you get a 2, get back $2. And otherwise, meaning if we have 3, 4, 5, or 6, we lose. We don't get anything back. Right, this is a fair dice. So the probability of getting a 1 is 1/6. Probability of getting a 2 is 1/6. Probability of getting 3, 4, 5, or 6 is 4 choices out of 6. Right, that's what we have. Now, if we pay $1 to play and get back $3, the total is going to be $2. And here we have $1. And here that's just -1. So now multiply across. 2 times 1/6. I get a fraction. 1/3. Now we have 1 times 1/6 is itself, so just 1/6. And now -1. -1 times 4/6. -2/3. Now I will add all this up. That number plus that number plus 1/3. 1/6. -2/3, 1/3, and 1/6. Right, -1/6. So this is the mean or the expected values, meaning that in the long run, every time we play, we lose -1/6. So about about 16-17 cents, about 16.67 cents. Right. So if we only play one time, it is impossible to lose this amount. But in the long run, each time we play, we expect to lose this much. Right. Once again, this doesn't guarantee the mean we get for a certain number of trials. It just say that in the long run, we expect to lose this much for each one of them, each time we play. Right. Here more example. A charity sell $10 raffle tickets for a chance to win $36,000 car. If 6,000 tickets are sold, what is the expected values for a person buying only one ticket? So this is the expected values from a person buying a ticket, not from a charity selling the ticket. So first, one is the outcomes. And there's the values. probability, and then the product. I should say values times probability. Right, outcome, either winning or losing. Simple as that. So win and lose. Values. Now this is expected values for a person buying one ticket. So when you buy the ticket, you have to pay $10 regardless, winning or losing. But when we win, we get $36,000 values of the car. And the probability, there's only one ticket, that is one winning ticket out of 6,000. So the win is 1 over 6,000. And lose is the complement to that. So 1 minus 1 divided by 6,000. It'd be one fraction. That's 5999. 5999 over 6,000. Now we multiply across. First the values. When winning, lose $10, but winning 36,000. And we have that times the chance for winning 1 divided by 6,000. So we have 5.998. Now the chance to lose, negative 10 times 5,999 divided by 6,000. Is negative 9.99833 something. Expected values is found by adding the last column. So expected value will be here. So if this number plus that number is negative 4. So that means expected values for each person when buying one ticket is negative $4. So if you only want to buy one ticket, it's never going to lose $4, right? It's either winning, which is a lot, $35,990, this much, or lose $10. Those are the only two outcomes. But in the long run, each time each ticket, we lose $4 each in a very long run. Now, so that is the expected values for one person buying the ticket. The charity, when they sell the ticket, one ticket, they get about exactly $4, because expected values of a person buying a ticket losing is the same as the expected values of the charity winning. So each ticket a person buying expect to lose $4. The person selling expect to win $4. It will be the same amount. Or another way we think of this is there's 6,000 ticket and 10,000 and 10 each. So if 6,000 times 10, so the total money 60,000, and then we have to subtract 36,000 for the values of the car. So the charity expect to get back $24,000, and $24,000 divided by 6,000 tickets. So each ticket they expect to win $4. So that's exactly as what we have earlier. So one winning, one losing, the same amount. Right, here's another example. An outdoor concert event usually makes 100,000 for an evening show. However, if it is raining, the event is cancelled. Make no money after that. Suppose the change for rain on the event is 30%. The planner of the event buys an insurance policy for $40,000, so that if it is raining, the insurance will pay $100,000. Right. From the insurance company perspective, what is the expected value of the policy? So once again, we have to look at the perspective to determine if it's winning or losing, gaining or. So the outcome here, there's only two outcomes: raining or not. So when there's rain and no rain, there's only two outcomes. Values, probability, and now we multiply those two. Right. Now that we know that the change for rain is 30%. Okay, that much we know. Or 0.3. And if it's raining, it's 30%. Not raining will be complement to that. 1 minus 0.3 is 0.7. Right, so we have the probability. Now the values. The planner buys an insurance policy for $40,000. Right? So from the insurance company's perspective, they will gain $40,000. Regardless of raining or not, because the planner paid the insurance company $40,000, whether it's rain or not. Now, so that's what the company will gain. However, if it rains, the company have to pay back $100,000. And if it's not raining, the company doesn't have to do anything. So those are the values and probability. Next, the values of 40,000 minus that. Of course, that will be negative 60,000. I'm not sure what we did. Just skip on the zeros here. Minus 100,000. As I forgot 1 0. Sorry. There. And then multiply 0.3. So negative 18,000. And when there's no rain, the company will get that much money. Doesn't have to pay back anything. $28,000. So the expected values when we add these two together, it's 10,000. So it's hard to say that in the long run the company will make $10,000 for such event. This is very strange things, because the company usually they don't sell a lot of this insurance because they don't have a lot of events like this to expect this. So it's very careful when we only have a few number of trial here. So if they have like 10 events on the same day and it rains, the company will have a bit trouble. But if the event on different day, the chance for raining or not is 30%. So in the long run, they expect to make $10,000 for a policy like this. But like I said, they don't have a lot of policy like this. The chance for the insurance company will only have a few insurance policy like this. So even though the average they make $10,000, but something happened and it ran for the whole month, and somebody buy policy for the whole month, the company will be in big trouble. But then again, but if there's no rent for the whole month, the company will make a lot of money. So, but then it's just a game of chance. In the long run, they make money, but only a few. In the short run, anything could happen. You sell bags 6 pies a day, that costs $2 each. I'm going to this farm. On 35% of the days, she sell only 2 pies. 38% of the days, she sell 4 pies. And the remaining 27% of the days, sell only 6. So once again, the first one is outcomes. Next we have values and probability. The outcome is actually not really important. I'm just going to have that there so we know what the values and probability corresponding to it. But in terms of calculation, it doesn't do anything. So values times probability. Right, outcomes. Sell 2 pies. So 2 at 35% of the time. On 38%, sell 4 pies. For 38% of the time. And 27% of the time, she sell only 6. Right, back 6 pie a day, the cost of $2 each. So cost $2 each times 6, so that is the cost -12. Doesn't matter how many she sell, that is what she have to invest toward $12. She invests $12 negative. Okay, so once again, this is the expected values for her, so that with respect to this person. Right, now if she sell 2 of them and set the price for $5 each, so she get $5, but she only sell for 2 pies. So the total of that -12 plus 10, so that is equal to -$2, right? So she invest $12 and get back only 10 because $5 for each pie she sells, so -2. Now, if she sell 4 pie and $5 each, so 20 minus 12, so that will be +8. And when she sell on 6, $5 each. So -12 plus 30, that's $18. So if she sell all 6 of them, she got $30 back, invest $12, so the net profit $18. Right, now we just multiply across. -2 times 0.35, -0.78 times 0.38, 3.04, and 0.27 times 18, 4.86, which is add all of this up. 4.86 plus that plus that, 7.2. So in the long run, expected values for each day is $7.2. So the profit of $7.2, and it will never happen in a particular day, but in the long run, the average will be 7.2. Because for a particular day, there's only 3 outcomes: lose $2, gain $8, or gain $18. Only those 3 outcomes. But in the long run, each day CMAX $7.2. Right, so that was expected values. Next, we have the standard deviation. So expected values is just like the mean. Now we have the standard deviation. Standard deviation is given by this formula. So let's look at the example. A lab order shipment of rats, 100 rats a week, 52 weeks a year from a rat supplier. Price for each weekly shipment of rats given by this. Find the standard deviation for the lab budget next year rat order, assuming this distribution does not change. Alright, so when we look at this, we have to determine which one do we put. If we use a calculator, the values will be list 1, the probability will be list 2. So list 2 is the probability. And when we have list 1, list 2, we can just do one variable statistic of the 2 lists. So let's do using the calculator here. Need to clear this first. Clear, and clear. Right. Now the values 10, 12.5, and 15. Corresponding probability 0.3, 0.25, 0.45. Right. So once again, probability in list 2, the values in list 1. Second more. Now we just need to do one variable statistic. Stat, calculate one variable statistic. List 1 and list 2, calculate. Right. So we want the standard deviation of this one is equal to 2.13. So we just say if we use one variable statistic, for this one and this 2, we have 2.13. Right. Next, we have this example. Compute the covariance following probability distribution. So the previous one we calculate the variance of the standard deviation. If we want the variance, we're just going to square that. Right. So again, list 1, list 2. I put this in list 1, put this in list 2, and then do one variable statistic. Get the standard deviation, square that, we get the variance. Right. Stat, edit to list 1, clear, list 2, clear. Right, the values 0, 1, 2, 3, 4. List 2, 0.06, 0.58, 0.22, 0.1, 0.04. Right, and stat, one variable statistic. List 1 is the values, list 2 probability, and then calculate. The mean is the expected values, the standard deviation is 0.899. So we just say route 2 standard deviation 0.900. If we round up, that's what we get. And in that case, so this is the standard deviation. Now the variance, we're just going to square this. As 0.81. But if we want the exact values, you can go to variable, the statistic variable, and we want the standard deviation, this one, right? And then we square that, and so the variance 0.8096. Right. So with that, we finish section 6.1. See you in another video in statistics. As always, thank you for watching.